Hello everyone, my name is Yuki and I'm a senior studying electrical and computer engineering.
Hi, my name is Noshin. I'm also a senior studying electrical and computer engineering.
So our research topic is on the effect of eccentricity and microwave imaging of multiple composite pipes. This work is related to the use of microwave imaging for inspection of multiple non-metallic pipes that are concentric or multi-layer concentric pipes. Traditional non-destructive testing methods like eddy current, ultrasonic testing, and more cannot be allowed for inspection of non-metallic pipes like PVC, FRP, HDPE that are commonly seen because the physics is based on metal components for these methods. Using these methods may cause major production failures or environmental mishaps. Due to that, our research group have already developed a non-destructive testing method for inspection of multiple composite pipes. The study of various parameters of multiple pipes using microwave imaging has been presented before, but one important factor has not been studied yet. Therefore, for the first time, we are studying this important factor, and that is the eccentricity of the pipes with respect to each other. In other words, we're trying to see what if the pipes are not perfectly concentric and their center has non-zero distance. What will be the effect of that on the images when we use microwave imaging?
Assuming our system is a linear system, those of you in engineering or related field would be familiar with the convolution theory. To define convolution, it's a method to combine two signals to form a third signal. Since we assumed our imaging system to be linear and space invariant, which lets us use convolution theory. Looking at the block diagram in our poster, convolution lets us get a response from an unknown input to the system as point spread function or impulse function. Signals have been sent through the defects to obtain point spread function, then near field holographic imaging has been implemented. Unknown shapes of the defect can be found by solving the system of equation by taking the Fourier transform of the system over phi direction. The response of unknown function can be obtained from the convolution of impulse function and the input function. Please refer to our paper for the details on this theory. Moving on to the results section, as mentioned earlier, our research was to study the effect of eccentricity. The setup which the simulation was performed included two circular pipes. The radius for the outer pipe was 40 millimeter, while the radius for the inner pipe was 20 millimeter. We had 13 antennas around the outer pipe, one of them being transmitter antennas, while the other 12 being the receiver antennas. Other parameters such as thickness, tangent loss, and relative permittivity of both pipes were similar. This model was simulated in UltraFeco software, which allowed us to experiment the effect of eccentricity with close approximation to real scenario. We added noise of 20 dB for realistic study. Our initial experiment included eccentricity of 0.5 millimeter on inner pipe only, with multiple defect angle. Those results were favorable, leading us to further our study on eccentricity. Eccentricity is the radius difference between the outer and the inner pipe. This experiment was done only changing the centricity of inner pipe with respect to outer pipe. To understand the effect of eccentricity, we experimented with eccentricity from 0.1 millimeter to 0.9 millimeter, which was simulated with defects at angle 170 degrees and minus 170 degrees on both pipe one at a time. If you direct your attention to the poster, you'll notice the two 1D images on the results section. Figure 4 shows the result of simulation with 0.5 millimeter eccentricity and the defect angle at 170 and minus 170 degrees only on inner pipe. On this image, the blue lines is the reconstructed image obtained from the simulation, and the red represents the ideal image. As it can clearly notice that the quality of reconstructed image is much deteriorated from the ideal image and also further from the ideal image. Figure 5 had the similar setup except it was simulated with 0.9 millimeter eccentricity on inner pipe The quality of reconstructed image received from 0.9 millimeter eccentricity was much more degraded than that of 0.5 millimeter eccentricity. Figure 6 on the top right corner shows an image how the error increased on inner pipe as the eccentricity increased. We also studied the effect of eccentricity on outer pipe directly resulting from changing the eccentricity of inner pipe. Please refer to our paper for the details on that experiment. Finally, we were able to observe the clear correlation between the error received from the eccentricity and how it increased as eccentricity increased.
In general, eccentricity is a very important factor, and from the results of our studies, the quality of the reconstructed images is highly sensitive to non-zero eccentricity, where even a 0.5 millimeter eccentricity can cause image deterioration. With the serious effect of eccentricity, we plan to further develop a technique to estimate the value of unknown eccentricity parameters and then try to reduce the effect of that on the images. This is an ongoing work that we hope to get promising results. Lastly, this work was supported by NSF and as well as ISRC, and we would like to thank Tech's Europe program and as well as Columbia University's CUSJ. Thank you.
Thank you.